Welcome to The Foundry by Forge College. Let's just jump right into it. In our last explainer, we accomplished something huge. We successfully integrated the consensus mechanism into the Firedancer architecture. We basically dropped a massive, high-performance engine right into the chassis of our validator. But getting it installed? That's really just step one. Today, we're talking about how to tune that data management engine so it runs with absolute pinpoint precision. Because the ultimate engineering question is this. We built the engine, but how do we make it actually purr? Right now, your consensus layer is just kind of sitting there. It's waiting on data fetches, serialization, and disk rates. And when those pipelines stall out, your end-to-end latency completely spikes and leader throughput takes a massive hit. So today, we are hyper-focused on squeezing out the absolute maximum operational efficiency from those data paths. And ideally, we want to do that without blowing the engine to pieces, right? We're officially shifting gears from just measuring the system to actively getting in there and optimizing it. All right, here's the roadmap for today's tune-up. We'll start with a quick pit stop, build out our optimization toolkit, establish a solid baseline, start turning some dials, measure the actual impact of those changes, and finally, go over some golden rules. So, Section 1, welcome to the pit stop, where we'll make sure we understand the core mechanics. If you think about our data management system, it's basically a high-speed conveyor belt feeding into a massive factory shipping department. And to tune that belt, we rely on a few specific concepts, starting with the batching window. You can think of batching kind of like carpooling, but for data packets. Look, instead of sending one person in one car 1,000 times, which obviously creates a massive traffic jam, we cram 50 people onto a single bus. It drastically reduces the per-message overhead and overall CPU load. Sure, the first person on the bus might have to wait a tiny fraction of a millisecond longer for it to fill up, but the overall throughput of our highway, it improves dramatically. Next up is backpressure. Honestly, I always picture backpressure as the toughest bouncer at the most exclusive club in town. When that consensus handoff queue gets packed, this bouncer enforces a super strict one-in, one-out policy. If the validator is getting slammed with heavy traffic, we literally cannot just let the system accept data endlessly. If we did, we'd hit unbounded memory growth and the whole thing would just crash. So backpressure signals upstream to slow down, and that protects the validator from getting totally overwhelmed. Okay, moving right along to Section 2. Let's build out our optimization toolkit. We're definitely not just guessing and checking here. We're going to use a highly reproducible bash script. Let's call it measure-data-opt.sh. Now, this script executes 3 mandatory stages in exact order every single time. Step 1, it collects baseline metrics. Step 2, it applies a single parameter change, like tweaking that batching window we were just talking about. And Step 3, it collects the post-change metrics. To pull this off, you're going to need tools like JQ for parsing JSON outputs, curl to query your telemetry endpoints, and, absolutely crucial, a proper staging environment. Which brings us to Section 3, establishing your baseline with fixed workloads. Before we even think about turning any dials, we absolutely must record how the engine runs in its default state. And we do this using a fixed 60-second workload. Look, if the workload changes between our tests, our data is completely useless. So during that baseline run, we capture some very specific telemetry signals. We want P50 and P95 latency to see the user impact. We want throughput to gauge processing power. We need CPU usage to understand the computational cost. And we want queue depth to reveal any hidden bottlenecks. Capture these numbers and seriously guard them with your life. Section 4, time to start turning the dials and actually applying our optimizations. This is where we actually inject an optimization, maybe expanding that batching window. But hold on, before you touch your keyboard, remember the absolute golden rule of tuning. Isolate one variable at a time. If you go in there and change 3 things at once and suddenly the system runs 20% faster, well, that's great, but you have no earthly idea why. Or even worse, if the validator completely burst into flames, you won't know which dial caused the catastrophe. One variable, period. Mechanically speaking, our script handles this in 3 really straightforward steps. First, it copies the newly optimized config file over to the Firedancer directory. Second, it restarts the Firedancer service itself. And third, and guys, this is crucial, it tells the script to go to sleep for at least 10 seconds. You have to let the service grab a coffee, warm up, reestablish its network connections, and fully stabilize before you blast it with your post-change workload test. All right, Section 5, measuring the impact by comparing the baseline against the optimized run. This right here is the moment of truth. We're comparing our baseline JSON artifact against our new optimized JSON to see if our brilliant engineering theory actually worked out in practice. If we look at a sample dataset, let's say our P50 latency dropped beautifully, going from 12.4 down to 9.1 milliseconds. That is fantastic. And maybe throughput ticked up slightly too, from 4,200 to 4,300 transactions per second. Also great. But what if the CPU percentage jumped from 72% all the way up to 78%? By tweaking our batching window, we did successfully reduce overhead and boost speed, but we definitely had to pay for it with more CPU cycles. And honestly, this brilliantly illustrates the classic engineering trade-off. We gained speed, which is exactly what we wanted for end-to-end operational efficiency. But our batching tweak cost us CPU. There's just no free lunch in systems architecture. You're always going to be weighing your service level signals, like latency and throughput, against your resource level signals, like CPU and memory. Which brings up a really critical question we have to ask when we're interpreting these results. Did the queue depth actually shrink, or did we just move the bottleneck somewhere farther downstream? If your block assembly queue depth decreased, awesome. You genuinely reduced contention at the consensus handoff. But if that queue depth increased, well, your optimization might just be processing data faster than the next subsystem can handle it. You basically just created a brand new traffic jam further down the pipeline. Section 6. Let's wrap this up with the golden rules and principles of tuning. Let's lock in these core principles. First, like we said, isolate one variable at a time so you can actually attribute cause and effect. Second, always measure both your resource constraints and your service outputs, because remember, speed usually costs you CPU. And third, always prefer reversible, incremental changes and test them in a staging environment first. Verify that you can roll back your config to its original state. Trust me on this one, verifying reversibility is exactly how you avoid getting angry, panicked phone calls from network operators at 2 in the morning. A quick but super important quality assurance note. Disciplined logging is absolutely mandatory. Double-check the spelling of technical terms like Prometheus, backpressure, JSON, and bash in all of your analysis reports. Having clear, precise documentation means another engineer can look at your output 6 months from now and actually understand it, instead of having to guess what you were trying to do. Professional engineering standards matter. Looking ahead, make sure to keep those JSON artifacts and summary files safe. In our next explainer, we're going to dive even deeper into measuring operational efficiency and debugging regressions. We'll use the exact same telemetry skills and JSON summaries we built today to hunt down downstream instability and pinpoint exactly what happens when an optimization accidentally causes contention somewhere else in the system. So, I'm going to leave you with a final, slightly provocative thought to ponder. When you tweak a system, are your changes truly optimizations, or have you simply shifted the bottleneck and made it someone else's problem downstream? True architecture requires seeing the entire board. I really hope you found this deep dive into Firedancer data management as fascinating as I did. To master more advanced Web3 concepts and continue building your expertise, be sure to visit forge.college. Thank you so much for learning with me today, and keep building.